Hey class, Mr. Moyedin here with a calculus video. This concept is called making a function continuous. The question here asks to find the values of a and b to make this function f continuous everywhere. You'll notice it's composed of linear functions, so it should be continuous everywhere except for perhaps where one function ends and the next function begins. This highlighter makes it harder to see, so that's great. So all that really means is we just need to focus on determining continuity at these handoff points, and that'll become clear in a graphical sense in just a moment. First, let's review what it means to be continuous in the first place. A function is continuous at a point, we'll call that point x equals a, if the three things following are all true. The function has to be defined at a, the limit approaching a has to exist, and as you approach a, you get the exact same value as you would at exactly a. The limit is equal to the value, meaning the previous two numbers that you get from both of these are the same. Let's see why that's the case, and also let's see some failures of this concept to help us demonstrate why continuity is defined in this manner. So I have three pictures here, and the top two are, as you can hopefully see, are discontinuous. You cannot draw each curve without picking up your pencil, and this bottom one here in the corner is continuous. So looking at the first one here in the corner, the top left, is the function defined at a? The answer is yes, because this dot right here exists. There's a dot. If there were no dot, if these were both open, then it would fail the first part, in which case there's no reason to continue. So this part works for the first problem. Does the limit as you approach a exist in that first picture? And the answer there is no. So in this problem we would have this so far, which means that it is not continuous, because all three have to check out. And the reason the limit doesn't exist is as you approach a from the left, you get this lower number, and as you approach a from the right, you get this higher number. Those numbers are different, and therefore the limit does not exist. Notice that in the next example on the right here, the limit does exist. So let's backtrack a bit. Is there a value at exactly a? The answer is yes, because this dot exists, or is defined to be precise. So that checks. Does the limit as you approach a exist? The answer is also yes, because unlike the previous example, as I get close to a from either side, my function approaches the same value, and that value is whatever this is. So the limit does exist, or in road and bridge terms, the roads meet. There is a bridge, the roads meet. However, as you can see here, the roads meeting and the bridge are not located in the same place, which is to say, the limit is not equal to the function's value at a. So this thing fails to hold. When you have continuity, as you can see here, for one, there's no funny business happening here, so there's no reason to mark it. But as I approach a, I get whatever this number is from both sides. And at exactly a, I get the exact same number. I have continuous behavior there, so all three things have to check out. So how does this help us with finding values to make a function continuous? First, let's make sure we actually understand piecewise functions now that continuity is hopefully in our bag. A piecewise function has three different, or depending on how many parts, a number of different pieces to it, hence the name. Where these pieces, this, and this, where these pieces are valid are determined by these categories. When x is less than -1, use the top function. When x is between -1 and 2, including -1, use this function. And when x is more than 2, use this function. So if you look carefully at the domain here, every part of the x-axis has a place to be sorted into. So that tells me that my domain is split into three regions. The first region is to the left of -1, but not including -1. The next region is including -1 all the way up to 2, but not including 2. And the final region is from 2, including it, all the way onwards. I'm going to try to keep to some of those colors here. I'm going to call this bottom one here green, this middle one orange, and this top one here, I'll call that red. If I can get the pen to work. Okay. 6x minus 2 is the function's rule when x is less than -1. So that's a very steep uphill positive increasing line with a y-intercept of -2, but it's only valid -1 and below, so, or below -1, so it's going to be something like this with an open circle here. The green function is valid onwards from 2, and its value is -2x plus 5, which is a y-intercept of 5 up here, a slope of -2, so that would look something like this, perhaps. Just a general picture. And in between there, in orange, is some kind of function. It looks like it's a linear function given its formatting here, but I don't know what a and b are, but depending on what a and b are, I would have some sort of function that does what I want it to. I want it to connect these pieces in this manner. I want to create that orange function. But a defines the slope, and b defines the y-intercept. So how I exactly come up with those parameters will help inform my construction of this missing function. So I need to connect these dots with the right parameters. To find them, we're going to examine the handoff points here at -1 and here at 2 to ensure that the red and the orange meet and the orange and the green meet. The red and the orange meet at -1, the green and the orange meet at 2. So this splits us into two problems. Let's first find continuity at -1. Continuity at x equals -1. As I approach -1 from the left, so I'm going to abbreviate here a little bit and also make my pen a bit smaller. As I approach -1 from the left, I'm going to be using the top function. Let me stick to my colors. That was orange, that was red. The middle one was orange, and the bottom was green. Different green. Okay. The red and the orange are the ones that are going to exchange here at -1. So -1 from the left would be a little bit less than -1, which would take me to the red function. So if I plug -1 into that, what I'm basically doing is I'm taking the limit as I approach -1 from the left. That would give me -1 in for x, so that would be this, minus 2, which is -8. At exactly -1, I would be using the middle function in orange because that's including -1. So plugging -1 in for x, not for a, for x, I would have this, which simplifies to -a plus b. And to the right of to the right of -1, that would be precisely where the middle function is also valid because it is -1 is less than or equal to x. So that would also be -a plus b. I'm using the exact same function, so why do the math again? For this to be continuous, all three of these must be equal. The left road, the right road, the limit exists. The bridge has to be equal to both, the function's value at that point. Which gives me a limitation, or a constraint. It tells me that a and b, or sorry, -a and b must add to make -8. Or to write this in a little more familiar form, -a plus b equals -8. That must be true in order for continuity to occur. It's kind of hard to read. -a plus b equals -8. Let's put this idea on hold for now and find what is happening at the other handoff point, at 2. At -1, we produced this restriction. Looking at the next handoff point, that would occur at 2. So graphically speaking, we figured out that this restriction requires -a plus b equals -8. We now need to figure out what does this restriction imply. So from the to examine continuity at x equals 2, I need to consider 2 from the left at exactly 2, the function's value at 2, and approaching 2 from the right. So 2 from the left is a little bit less than 2, aka this function. So in orange that would be a times 2 plus b. At exactly 2, that would be this function here because it's greater than or equal to 2. The or equal to part there is important. So that would be plugging in 2, negative 2 times 2 plus 5, which is negative 4 plus 5, which is 1. And 2 from the right is also that same function in green, so I'm going to get the same thing. For continuity to occur, let me go ahead and simplify the orange. All three of these, the left road in orange, the bridge in green, and the right road in green, all must be equivalent. So I now have, and this obviously is true, this is now a second restriction. 2a plus b must make 1. So I now know the requirement for this to occur at negative 1. I have just figured out the requirement for continuity to occur at 2. And those two restrictions together give me the last leg of the problem, the key to actually finding these values. So here are the two restrictions that we've just determined. At this point, the original function actually isn't super important. We can use these pieces here in black to solve the original question to make it continuous. What we have here is a problem from algebra class called a system of equations. There are two variables, a and b. There are two equations, so this is a solvable system of equations. One popular method of solving such a system is to use something called substitution. It's not the only way. Elimination is another popular method, but substitution is often a quick and easy approach. So using substitution, I'm going to solve one of my equations, probably the top one, for one of its variables. So if I take this top equation, I can rearrange that to say b equals a minus 8. I can then substitute that in place of this b right here. So the bottom equation becomes 2a plus quote-unquote b equals 1. So I'm substituting a minus 8, which is b, in place of b in the other function. This gives me 3a equals 9, or a equals 3. I asked to find a and b. We have just found a. We can now find b, because b is a minus 8. So b is 3 minus 8, or b is negative 5. Hope this helps.